Part 2, prime numbers and prime factorization. This part is the most difficult part of lecture number 3. Hopefully, we will explain the difficulty in here through the practice problems. Property number 1. A prime number is a positive integer that is divisible only by 1 and the number itself. A compositive number is a positive integer that can be divided by more than 2 positive integers, one itself and something else, at least a third number. This means that a number is compositive if it is divisible by some positive integer besides 1 and the number itself. For example, 2 is a prime number that can only be divided by 1 and itself. 4 can be divided by 1, 2, and 4. Therefore, 4 is a compositive number. 2. If a number is not divisible by a prime, then it is not divisible by any multiple of that prime. So, in testing whether or not a number is prime, we only need to test if that number is divisible by prime numbers. To check if a number is prime, we only need to test if it is divisible by primes whose squares are less than or equal to that number we are testing. So we'll go through these properties when we look at the practice problems. Last one, every positive integer has a unique prime factorization. Okay, practice problem 5. A. Can you specify the listed numbers are prime or composite? So there are 5 numbers. The first number, 61, is a prime number. So it can only be divided by 1 and itself. The second number, 143, is a compositive number. 143, if we divide it by 11, you will see that it's 13. So therefore, 11 multiplied 13 equals to 143. So 143, it has 4 factors, 1, 11, 13, and itself. And the students can go over the rest of the numbers to see whether they are prime or composite. The definition are in the previous page. B, find the largest 2-digit composite number in which both digits are prime. Okay, we are talking about digits in numbers, so we only have 0 to 9 as our choices. So for prime numbers within that range is 2, 3, 5, and 7. Okay, among these numbers, what would give us the largest number? So we start from the largest number, and we could end with the largest number as well. So therefore, we get to the largest 2-digit composite number. 77 is a composite number, right? It can be divided by 1, 7, 11, and itself. B. C. Find all pairs of prime numbers whose sum is 61. So there are 2 ways of doing this. All the prime numbers between 1 to 61, we can list them out. So starting from 2, 3, 5, 7, 11, and so on, all the way to 61. Then we reverse the sequence. So because we want the pair to add up to 61, so 2 can only be added to 59. So the sum of the 2 is 61. So for 3, it can only be added to 58. But this is not possible because this 58 is not a prime number because it can be divided by 2 also. So in this way, we can find out all the pairs. So for 61, we cannot go 61 because 0 is not a prime number. We can only go all the way up to actually 59. And why is that? So if we have 60 as our largest number, and 60 has to add to 1, but 1 is not a prime number. So the top row can only go up to 59. So 59 will add to 2. 2 add to 59, this pair will work because 2 is a prime number. 59 is also a prime number. You will see that all these numbers, the bigger number, prime numbers, has to be odd numbers. If they're even, they must be able to be divided by 2. So therefore, they won't be prime numbers. But these odd numbers, when they add to something to give you an odd number, this has to be an even number. So all these wouldn't work out, except the 2 and the 59. So there is only one pair, 2 and 59, that would give you a sum of 61. Both are prime numbers. Practice problem 6. Find the prime factorization of each of the following numbers. So we'll use one as an example, and the rest we hope the students can figure them out. For example, 30. 30 equals to 15 multiply 2 equals to 3 multiply 5 multiply 2. So 3, 5, 2, they are all prime numbers. Therefore, this is the prime factorization of 30. So the students can follow the same way. You don't have to get to all prime numbers in one single step. For example, like 288, it's going to take a few steps before you get there, and that's okay. For example, you can do 2 multiply 144, 2 multiply 2 multiply 72, and so on. It takes several steps until at the end you would like to give 2 to the power of something multiply 3 to the power of something, for example. I think the students can figure this out. Problem number 7. Paul multiplies 2 positive integers and gets a product of 16,000. If neither of Paul's integers ends in 0, and what is the sum of Paul's integers? So for this problem, we can first decompose 16,000 into, so it's going to take a few steps before the students get there, but we're going to write this out. 2 to the power of 7 multiply 5 to the power of 3. The problem says neither of Paul's integer ends in 0, so 2 and 5 cannot be mixed together. If 2 and 5 in one number, 2 multiplied 5 is 10. So that number must end in 0. So this has to be one number. This has to be in a different number. Therefore, this is number 1. Say this is number 2. And then the students can figure out what's the sum of Paul's integer.